This is a segment display powered by air. It morphs its silicone skin, can show numbers, and tell the time. Inside, tiny air channels perform logic. And while building, I accidentally created pneumatic RAM. Part of this video is sponsored by PCBWay. On this channel, we've built many air-powered robots and squishy machines. One key insight was to integrate small air channels directly into their 3D printed bodies, distributing pressurized air to their muscles. Inspired by microfluidic circuits, we moved from distribution to computation. By integrating vacuum-powered transistors and resistors, we built logic gates. And eventually, a ring oscillator that started working powered by a single flow of air. Finally, we used that pneumatic logic to build an air-powered dot matrix display, using multiplexing to control its pixels. Solenoid valves provide specific pressure inputs to the rows and columns. Those pressure inputs are decoded by the microfluidic logic. This way, we can control 16 pixels using only 8 inputs. After that vacuum dot matrix display, many of you suggested building a segment display and turning it into a clock. So to explore what's possible, I decided to accept the challenge. Let's first look at how an electronic 7-segment display works and steal one of its tricks. On the front, you see 4 digits. Each digit is made of 7 segments. But to control them, it uses much fewer pins. So how does this work? Each segment is just an LED. If we connect it between positive and negative, it lights up. Now here's the trick. We can select which segments light up by switching one wire. And we can build numbers by turning several segments on at once. If we switch the other wire, the number moves. By using 4-digit and 7-segment, so 11 inputs in total, we can control 28 segments. This I wanted to replicate using air. To display 4 different numbers, the electronic version rapidly toggles through the digits until they appear constant. But air is slow. Instead of relying on speed, maybe we can rely on memory. In the dot matrix display, each pixel was latching. Once activated, it maintained its state. This simple idea turned the display into memory. For the final look of the clock, I had a specific vision in mind, a bright orange membrane embedded in a translucent enclosure. Which brings me to today's sponsor, PCBWay. And you might already know this, but PCBWay offers more than PCBs. CNC milling, 3D printing, sheet metal and more. To create an enclosure, I went with their resin printing services. Ordering was a breeze. Simply upload your file and get an instant quote. A few days later, a package arrived. Carefully wrapped inside that package, a beautiful enclosure. I love that frosty translucent appearance. This will be perfect for housing the display and all its components. I will definitely order again at PCBWay. Now we just need to fill it with life. Let's start with a single segment. They function much like the pixels from the dot matrix. A printed body. To reduce print time, I switched from a 0.2 to a 0.4mm nozzle. Around the perimeter of the segment, I added a raised edge. To cast the membrane, I designed a 2-part mold with a recess. After casting and demolding, the recess has formed this little lip. And that is critical. You see, I added one more element to the design, a clamping frame. We first wiggled the frame over the lip before placing the membrane on the body. When the screws are tightened, it pulls the frame down, clamping the lip in between and creating a tight seal. Now, if we pull a vacuum, the segment is sucked in and remains in this state. In this way, it can hold 1 bit of information. A bit can be either 0, which for our system is atmospheric pressure, or it can be 1, represented by vacuum. This is our memory, but to use it, we need to add one more component, our vacuum transistor. Inspired by microfluidics research, we designed a microvalve that opens when vacuum is applied. A soft membrane is sandwiched between 2 3D prints with integrated air channels. The transistor is normally closed. If we connect vacuum to one side, it only pulls the membrane tighter. But apply a vacuum to the control and the membrane is pulled away, enabling air to flow across. By connecting the segment and transistor, we build our basic memory cell. To use it, we need to provide data. In this case, vacuum, or 1. Then, by opening the transistor, the data is written to the segment. And because the transistor is self-sealing, even after I remove the input, the state is maintained, until we write a new state. Now, onto the full digit. It is composed of 5 layers: a display membrane, a clamping frame, the main body, a logic membrane, and a write enable controller. 7 of our memory cells, each composed of 1 transistor and a segment, form a 7-bit memory array, the full digit. Pressure inputs enter from the left, our data. All transistors can be opened using a single input. I call it the write enable. Once the write enable receives vacuum, all transistors open and the data is written to the segments, hence the name. And a number appears. Let's make it real. One key trick is to make use of the build plate. The surface printed against it becomes quite flat. That flatness is critical for sealing. But my build plate had seen better days. To get an even smoother surface, I switched to glass. After 8 hours of printing, here it is, the digit body. It is pretty transparent, but switching to the larger 0.4mm nozzle seems to reduce it a bit. You can still see the channels inside. And the surface came out great. It is so shiny, almost mirror-like. To access the channels, we hammer in the blunt needles. Next, to the write enable. This one also came out great. The super smooth surface should enhance the sealing a lot. Now, onto the squishy parts. For casting the logic membrane, I came up with this new technique. 4 layers of tape on each side. Then pour over the silicone, flatten it, and spread it out using a ruler against the tape. After curing, we can take it off the glass and start cutting out the membrane shape using a mask. Finally, punch out the screw holes. Let's add the logic membrane to the write enable. Clean the surface, align the membrane, then press it on. To the write enable, we add a solenoid valve and the vacuum supply. Finally, we remove the mask. Look closely what happens when I energize the solenoid. Vacuum enters the write enable and pulls down the membrane. This single input opens all 7 transistors. This seemingly simple principle is what makes the whole logic work. Next, casting the display membrane. It's very thin and feels quite delicate. Time to assemble the full stack. First, the display membrane, followed by a clamping frame and the main body. At this point, we have to tighten the clamping mechanism to seal all segments. And finally, we add the write enable and solenoid valve. Now let's see what this thing can do. The 7 blunt needles on the left are our data inputs. At atmospheric pressure, they are all 0. So when I activate the write enable, nothing happens. But let's give it a different data input. Using this manifold, when I cover the top, it outputs vacuum to 3 of the inputs, turning them into 1. Now when I activate the enable, the data is written to the segments, and they maintain their state until a new data input is written. This is our memory array in action. With the right input, we can display a number. Now that we have the basics figured out, let's build our full display. The design is based on the same architecture, scaled to 4 digits. So how does it work? The data inputs enter from the center and branch out into 7 common data lines. Along the data lines I place the 4 digits, connected via transistors just like before. Each digit has its own write enable. To display 4 different numbers, we start by providing the data input for the first digit. Then activate the enable and the data is written to the segments. By repeating the sequence for each digit, we can write 4 different numbers. But to turn it into a clock, we need to add the dots. How should these be activated? As this is not already complex enough, I wanted them to appear whenever we write data to a digit. So every time one of the 4 write enable is active, the dots should appear. But if we simply connect the dots and all enable, we would destroy their function, as we could no longer write to a specific digit without activating all others. To solve that problem, I came up with a new vacuum logic building block. A one-way valve. Air can flow only in one direction. The membrane has a small opening. When vacuum is applied from one side, the membrane is pulled in and seals itself. But when applying vacuum from the other side, it is lifted and air can flow through the opening. By placing one of these between each enable and the dots, we can isolate them. And this finishes the design of our microfluidic circuit. Now let's make it real. It took about 30 hours to print, but it looks so good. All the channels on the inside. It's almost like a PCB, but for air. And the surface is so shiny. Using glass as a print bed is the way to go. Now to the display membrane. It's so orange. Let's get it out of the mold. Quite a delicate piece. We can start building the stack. By now you know the drill. First the display membrane, followed by the clamping frame and the main body. Then we have to seal the segments using that clamping mechanism. Next onto the 4 white enable and the data in. Printed them out and cut their membranes. Finally, we place them on the stack, always cleaning the surface with tape. This is a full microfluidic display assembly. It is made from only 3 materials: PLA prints, stainless steel screws and silicone membranes. But for it to display something, we need to provide specific pressure inputs. For that we mount the solenoid valves and their drivers. There are 11 solenoids in total, 7 for the data input and 4 for the white enable, much like the electronic version we looked at earlier. Finally, we can add it to the enclosure and add the power supply, microcontroller and vacuum pump. Now with everything in its place, let's give it power and find out what this thing is capable of. We can start with a single digit. Each of the segments can be turned on and off. The dots dance every time we write to the digit. Next, let's try writing some numbers. This looks so good. Let's move beyond a single digit. First, by writing the same data to several digits in parallel. Now let's try the real test. Writing different data to each digit. This works perfectly. Next I coded some fun patterns. This one I call the conveyor. Then a breathing mode. And Newton's cradle. Their rotations. And popcorn. While 7 segments are a bit limiting, I had to try writing letters. And obviously, I tried to write some short words. Well, let's move into what it's actually designed for, as a timepiece. By strictly refreshing 1 digit per second, we can display the time. This way the dots blink for every second. Though in this mode it's a bit slow when the hour changes, but that's fine for me. I also implemented a leading edge zero suppression, and I dig that look. Beyond telling the time, it works as a stopwatch, showing minutes and seconds. And lastly, it can run a countdown. When watching this display in action, it's easy to forget the complexity behind. I am still amazed by the fact that it works, but is it really RAM? A random access memory? Well, it can store a state, atmosphere or vacuum. You can switch between 4 memory arrays, the digits, making it addressable, and you can write different states into the memory. While our system itself cannot read the state, we can read it with our eyes. It's visible memory in action. So in my opinion, all that together makes it RAM. Or what do you think? Let me know what else I should build with this tech, and subscribe to not miss it. See you in the next one, and stay soft.